Hello, my name is FARRISHAH AQASHAH bin FAZLI. My matrix number is 01DAD23F1064.
Hi, my name is Muhammad IRFAN MUIZZ bin MAHADI. My matrix number is 01DAD23F1052.
Hi, Assalamualaikum. My name is SHAHRUL Azan bin AZMI, and my matrix number is 01DAD23F1054.
Now for the introduction. Vehicle dynamics is the study of how force and motion affect a vehicle behavior during movement. It focuses on factors such as acceleration, braking, cornering, and stability. This study analyzes how design parameters like mass distribution, center of gravity, wheelbase, and aerodynamic influence vehicle handling and performance. Understanding the aspect help engineers design vehicles that are safe, stable, and efficient while maintaining comfort and control under different driving conditions. Okay, next is for objective. First, to analyze the force acting on a vehicle under various conditions. Second, to understand how vehicle dimension influence dynamic behavior such as acceleration, braking, and cornering. Third, to compare different vehicle model and identify factors affecting their stability and performance. Fourth, to apply theoretical concept of vehicle dynamic in a practical case study and presentation. Okay, this specification have a three type of car has been choose like hatchback, sedan, and SUV. For the hatchback is Volkswagen Mark 5. For the length is 4.246 and the weight is 1.759. For the sedan is Mitsubishi Evo 9. The leg is 449 and the weight is 177. And the third is about SUV Porsche Macan. The leg is 4.784 and the weight is 1.938.
Alright, so this is our calculation about drag coefficient vehicle. So uh, it followed by a type of car. So given velocity 100 to 200 meter per second. For a drag force, it is given from the data. So we just take the data and put it on the drag force. So for a frontal area, so for the formula for frontal area, we use 75 over 100 times length times weight. So the total we gain for a frontal area for all of velocity is 5.602 meter square. For air density is we already know the it is given is 1.225. For a drag coefficient, we use a formula d a equals 1 over 2 times rho v2 v square times cd times a. So the coefficient drag we gain 0.094. So that's mean for the all velocity, uh, we calculate according to the all velocity, the total is same, where the total is 0.094. So that is a drag coefficient for a Volkswagen MK5 R32. So let's move on to the drag coefficient Evo 9. So it's the same, the data given uh, for velocity is 100 to until 200. The drag force also same from the data from the lab sheet. For a frontal area, is we use also the same uh, formula, where is 75%, 75 over 100 times length times weight. So for a frontal area, we gain a 5.96. For a density, we know is already given 1.225. And for a drag coefficient, we also use the same formula where is a dA equals to 1 over 2 rho v square times CD times A. So the drag coefficient we gain for Mitsubishi Evo 9 from velocity 100 to 200 is 0.087. Now we move on to a calculation about a Porsche Macan. So, uh, so it's still the same. Velocity is given from 100 to 200 velocity meter per second. Same also with drag force. Frontal area we use same formula where is 75 over 100 times length times weight. For the the density, uh, we know the air density is 1.225, and for a drag coefficient, we know we use a same formula as a Volkswagen MK5 R32 and Evo 9. So the formula is dA equals to 1 over 2 rho v square times CD times A. So the total for drag coefficient we get is 0.076 from 100 to a 200 velocity. For a frontal area, we gain 6.954 from 100 to a 200 velocity meter per second.
So today I'm going to explain about our graph, which is over here we have three types of graph. Which is the first graph is Volkswagen MK5 RTT2 drag force and velocity, and the second graph is Mitsubishi Evo 9, and the third graph is Porsche Macan. So the first graph is for the first Volkswagen MK5 RTT2. Uh, it stood up at starting 100 velocity, which is at 250, and then at 110 it stood up again at 300, and at 350 drag force at 120 velocity, and at 140 velocity it stood up at 450 drag force, and then at 500 drag force it's at 150 velocity it stood up to 500 drag force, and at 160 velocity it stood up to 650 drag force, and at 180 it stood up to 700 drag force, and 190 velocity it stood up to uh, 800 drag force, and finally at 200 velocity it stood up at 1000 drag force. So for the Mitsubishi Evo 9, at 100 velocity, starting at 250 drag force, and at 110 it going up to 300 drag force, and at 120 it's also stood up at 350 I'm sorry 360 drag force, and at 140 stood up to 450 drag force, and 150 stood up at 500 drag force, and 160 it's continued to stood up at 650, and 180 velocity it stood up to 700 drag force, and at 190 velocity meter per second stood up at 900, and finally for this Mitsubishi Evo 9 stood up to 1000 drag force. And based on the Porsche Macan, it start at 100 velocity at 200 and 230 drag force, and at 110 it's going up to 300, and at 120 it's going up to 370 drag force, and at 140 it stood up at 420 drag force, and at 150 it stood up to 570 drag force, and at 160 it's continued to shoot up at 650, and at 180 velocity it's going to stood up at 700 drag force, and at 190 it stood up to 900 drag force, and last but not least it's at 200 velocity it stood up to 990 drag force.
So for a result and discussion we do from our case study. So the study that we found that a vehicle weight, wheelbase, length, and aerodynamic greatly influence stability, handling, and overall performance. So it's mean the heavier vehicle like SUVs show better stability but require more braking force, while lighter vehicles such as sedans and hatchback offers better cornering and faster response due to their lower center gravity. Aerodynamic design also play an important role as vehicle with sleeker shapes experiences less drag, improving both fuel efficiency and stability. So, uh, from the slide it says improving both fuel efficiency and high speed stability. So from this it means uh, when the airflow and the aerodynamic is good towards a car, it means the engine from a car are not stressed to take a force from a wind current, so that uh, the engine are not stressed. At the same time, the fuel can be more efficiency. Also, it can gain a high speed without draining uh, an oil in the car.
And for the conclusion for our case study is the study concludes that vehicle dynamics plays a key role in determining a vehicle's performance, comfort, and safety. Factors such as weight, distribution, wheelbase length, and aerodynamics strongly affect acceleration, braking, and cornering behavior. Lighter vehicles like sedan and hatchbacks offer better handling and quicker response, while heavier vehicles such as SUVs provide more stability but need greater braking force. Aerodynamic design also improve fuel efficiency and stability at high speeds. Overall, this study shows how we gonna understanding vehicles dynamic, helping engineers design safer, more efficient, and well balanced vehicle.